Okay, so now time has come to start the fourth JSCE concrete committee webinar, Frontiers of Concrete Technology. So I'm Hayato Takahashi from Tokyo University of Science, Japan. So I'm in charge of chairperson of today's webinar. So it is a great honor to be welcome for many attendees and to famous researchers. So before start that, let me inform you the today's schedule. So at first, I will introduce the introduction of this webinar. So after that, two invited researchers present today's topic with including short Q&A. After that, more deep panel discussion will be held, moderated by Professor Asamoto from Saitama University. Then I will close this webinar. So at first, I will introduce the host of this webinar, JSCE. So JSCE, Japan Society of Civil Engineers. This is one of the Japan's biggest associations for civil engineers, including researchers and technicians. So this was founded in 1914, more than 100 years history, and is having more than 38,000 members currently. So this association is doing many activities and announces their information overseas by using English homepage, Facebook, and newsletter from international activities centers. So if you have interest, please feel free to access them. So this is the overall JSCE's introduction. And JSCE also has a research department for specific research field. And the concrete committee is one of the research committee which is holding this webinar. So our committee is involving the technique and science of concrete engineering. And one of the biggest issues is the addition of standard specification for concrete structures. So parts are mainly divided into design, materials and construction, and maintenance. And these were revised every 5 years to include and add the new knowledges. So English version of these specifications in 2007 version are now available freely online version. And summary version in English will be published in a few years. And we are disseminating the information using newsletter like this. So these letters are distributed 3 times a year, and you can get the recent activities, including research activity or public relations. And international seminars are also held once a year. Before the COVID-19, the seminars were done in the host country, like these pictures. But in recent days, this has shifted to online version like this, thanks to the IC technology. But actively, we are expanding the recent research activities. So this is a brief introduction of our organization. And again, today we are happy to hold the fourth JSCE FCT seminar. And so far, we had already 3 times like these seminars. First time at last year, April, we launched the first webinar, invited Professor Ueda and Professor Dai in relation to FRP composites. Second time, we invited Professor Maruyama and Dr. Miguel Ferreira from Finland, which focused on the aging management of concrete structures in nuclear power plants. moderated by Professor Nakarai. And as for that third times, we held the webinar about simulation of concrete and reinforced concrete structures using discrete analysis models, thanks to Professor Boranda from UC Davis and Professor Nakamura. And if you have interested in the past seminars, please visit the YouTube website and search for these keywords. So you can find out easily, I hope, and you can watch them again. Okay, then it will start today's fourth JSCE webinar topic, which is titled as Application of X-ray Computed Tomography for Concrete Durability Research. We are inviting the two leading researchers. One is Professor Sugiyama from Hokkaido University, Japan, and the other is Professor Promentilla from Salle University, Philippines. So after their presentation, follow-up panel discussion about this topic will be held, moderated by Professor Asamoto. So it will start soon, but during the presentations, if you have any comments or questions, please use the Q&A function, which you might find it in the bottom of the screen like this. So please write down your name, affiliation, and comments or questions. But we are very sorry for that. We cannot answer to your all questions due to the time limitation based on the past experience. So we can pick up only a few questions from the table. Thank you for your understanding. And in addition, we are also preparing the YouTube live streaming. So if you have any troubles to connect to Zoom URL, please try to use this YouTube URL to watch it. So, and same as the past seminars, this will be published on JSCE channel. So you can see a seminar after this event. So at first, the presentation will be given by Professor Promentilla about this topic. But before that, I will introduce the brief biography for him. So Professor Angelo B. Promentilla is now a professor of chemical engineering and the head of the Waste and Resource Management Unit of the Center for Engineering and Sustainable Development Research at Salle University. He received his PhD degree in Social Environmental Engineering from Hokkaido University in 2006 under the supervision of Professor Sugiyama. And after going back to Philippines, he was recognized in 2013 as one of the outstanding young scientists in the field of social environmental engineering by the Philippine National Academy of Science and Technology. And recently, he is a recipient of multiple scientific awards from the Commission on Higher Education, and National Research Council of the Philippines, and the Japan Concrete Institute. And he is actively involved in mentoring young researchers and the founding head of the Geopolymer and Advanced Material Engineering Research for Sustainability Lab situated at Salle University. So therefore, he is familiar with Japan based on his history, and currently one of the leading researchers for the materials chemistry and engineering. Okay, so Professor Promentilla, could you start your presentation if you are ready?
Thank you, Takahashi-san, for the very kind introduction. Please allow me to share my screen.
Okay, maybe you can share screen now.
Can you see my screen now?
Yes, no problem.
Okay, thank you. So again, it's a pleasure to be here and be a speaker of the fourth JSCE Concrete Committee webinar. I'm Mike Promentilla from De La Salle University. So first, let me ask you a question to poke your curiosity. Could you find connections from these 4 images and guess the unknown 10-letter word to describe what I have in mind right now for the story of my presentation? I'll give you a few seconds. Perhaps you can type it in the chat box or the Q&A just for fun. One example, maybe the word connection is appropriate to describe these images. Or tortuosity, which is, I don't know if you are familiar with this word, but hopefully at the end of my presentation, you will become more familiar with it. Or maybe the grayscale image or CT scanner, if you are familiar with the faces in these images. Or possibly tomography, which I hope through this webinar, I can explain to you the importance of this technique. And finally, maybe it's just hairstyles. So this is me and my hairstyle sometime around 2007. It's about 1.5 decade ago when I was a postdoc at Hokkaido University under the supervision of Sugiyama sensei. And the story of my presentation today will describe you my journey in trying to find out some answers from these 2 questions presented in this slide. How could I apply X-ray computed tomography to provide insights about cement-based materials? How could I make sense of the CT images of the material of interest, which in this case is actually concrete? And we should start with this timeline. Now, let's go back to 1895, when a German scientist named Wilhelm Conrad Röntgen produced and detected X-ray, which earned him actually the inaugural Nobel Prize winner in physics in 1901. Professor Röntgen was both a mechanical engineer and a physicist. And what you see here is actually the first application of X-ray. This is actually the radiograph of the hand of his wife. And of course, it is also important to know the theoretical aspect of the topic, which is in this case, I would like to introduce to you the scientist, the mathematician, Professor Johann Radon. Because sometime around 1917, more than 2 decades after the discovery of X-ray, an Austrian mathematician provided us the mathematics to reconstruct a cross-sectional image from the projection data, or what we call right now as sinogram or radon transform data. Professor Radon introduced this integral transform, which became the theoretical foundation of tomography. And tomography is an imaging technique by sections or sectioning that uses any kind of penetrating wave, such as X-ray. So this you can see here, tomo means cut, and we can see the cross-section through this technique. And of course, in the early 60s, a South African American particle physicist named Professor Alan Cormack published 2 papers that provide the theoretical underpinning of computed tomography for radiological applications. In fact, this is just a side project from his sabbatical leave. And as you can see, why this is important? Because this is actually become the theoretical foundation of what we refer to as computed tomography. But let me interrupt you with arts. I hope some of you is familiar or know this legendary rock band. Because in the same time period, the 1960s, if you are in the same age group of my father or me, you know that this is Beatles. And on September 4, 1962, roughly, it's 6 decades ago from now, no, the Beatles recorded their first single, Love Me Do, at EMI Studios at the Abbey Road. So you might be wondering why this is part of my presentation. Because as you can see here, no, this favorite band of mine, no, is connected to EMI or the EMI records. And EMI is the mother company which actually produces the first CT brain scanner. And the inventor of this CT brain scanner is no other than engineer Godfrey Hounsfield. He's an English electrical engineer, no, who's working at EMI and first imagine the possibility of this CT scanner. In fact, no, this first brain scan is in 1971, and after a couple of years, he shared the 1979 Nobel Prize for Physiology or Medicine with Dr. Alan Cormack for developing this diagnostic technique known as CT scan. In fact, there's an urban myth saying the profit earned by the EMI from Beatles is used to fund the research of Hounsfield and team. Again, just to clarify, it is just a speculation. But you can see the story on how this CT scanner, which has revolutionized, no, the field of medical diagnostics and health science, will be useful as well in the field of concrete science and engineering. And of course, let's us go back to at least the time during my postdoc, wherein I was able to read this paper of Dr. Yoshita Nakashima on the possibility of measuring tortuosity. And I'll discuss this later, no, using the X-ray CT image. But he applied this to porous rocks. Dr. Nakashima is actually a Japanese geophysicist in AIST, and his paper is one of my important reference to my work on X-ray CT. So as you can see, no, let me paraphrase Newton again. If I have seen through X-ray further and deeper, it is by standing on the shoulder of these mathematicians, scientists, and engineers. That's how science progress, and theory works hand in hand with practical feasibility. It will move our scientific knowledge toward to a practical application. And in this case, I hope, no, through this short talk, I was able to convince you the potential application of X-ray CT to study cement-based materials. And of course, I would like to acknowledge Sugiyama Sensei and my other collaborators like the faculty staff and former students from the Environmental Engineering, Material Engineering Lab at Hokkaido University. Special mention as well to our industry partner during that time, Obayashi Corporation, Dr. Hitomi and Dr. Takeda, who help us, no, to have access on one of the state-of-the-art synchrotron facility in Hyogo, Japan. And through this collaborative work, I was able to publish a paper in Cement Concrete Research, which is actually one of the most highly cited paper in my career. And this topic, as you can see here, is in fact, no, though it has been done a couple of decades ago, and I think it's still advancing, there is still many opportunities, no, on this topic on application of X-ray CT on concrete durabilities. So first, let me convince you why X-ray CT is a important tool for us to study concrete. In fact, it becomes now a routinary tool. No? Maybe more than a decade ago or 2 decades ago, it's still emerging. But you can see that it's a form of X-ray microscopy wherein it allows us for a non-invasive and non-destructive imaging of the internal structures at this high resolution, typically on the micrometer level. And through this approach of tomographic reconstruction, we're able to build 3D images. So the three-dimensional information is very vital for us to study further this kind of material. And of course, just like its application in medical science, trying to see, no, the defect or the problem, the health problem, through proper diagnosis, we can apply this as well to concrete. And you can see its advantage, no? Because of the depth of view, no? That it can cover, which give us some three-dimensional information compared to the other microscopic techniques. It can also provide a spatial resolution that can be interesting, no, for us to study. For example, the pore space, the cracks and the voids, and even those particles in this hydrated cement system. And possibly, no, in the coming years, the spatial resolution will become better and improve, wherein it can interface or complement with the much higher resolution techniques like scanning electron microscope and TM or transmission electron microscope. So this is an interesting field that we can look at. And of course, we need, no, to understand some basics of this X-ray CT system. So here is just a typical example of an X-ray CT system. It can be described by different components like primarily the type of X-ray source, the beam geometry. It could be conical, okay, or cone beam type geometry, or it could be a parallel beam geometry, depending on the X-ray source. It can also look at the type of detectors. It will detect the intensity of the transmitted X-ray, and of course that we need to be translated from the X-ray, no, to the visible region, because we need, of course, to record this in a digital image in the form of, for example, projection images. And of course, to reconstruction algorithm, we can see the cross-section from these projection images. And as I have mentioned, this can be done because of the previous studies, both theory and applied science, on how we can use X-ray to see the internal microstructure. So we can see, no, that this part, if you can look at this sample placed in a stage wherein it is being rotated, because to get a proper view, or let's say a very good image of the cross section, we have to look at different viewing angles. That's why it is being rotated, as you can see from this slide. In such a way, we can generate several projection images, and that would give us a more accurate imaging of the cross section. So just to understand the basic, no? Because I assume that most of you have heard this for the first time, or maybe not so much knowledgeable on this topic. So just to introduce you some jargons. No? So when we refer to as this slice, no? This is actually a one cross section, and you stack up, produce the 3D image. And we are looking at the slice as an array of voxels. Your voxel is your 3D pixel in your digital image. No? If you're familiar with your smartphone image, you have pixel, right? But in this case, you are looking at the pixel with thickness, and we call that as voxel. And of course, no, to give you an idea on how this projection image can be used to see the cross section through tomographic reconstruction, this is just an example, as you can see here, of a simple 4x4 cross section. We have a 4x4 pixels, and of course, this is just an illustration of your 4 projection data, as described by these 4 equations. We have 4 equations, 4 unknowns, which these unknowns are the linear attenuation coefficient. So technically, we are mapping the linear attenuation coefficient through X-ray CT. And in this case, through tomographic reconstruction, I'll not give the detail of the mathematics, but the idea is from this projected data, as you can see from this animation, the sinogram, no, can be used, no, through the back projection technique, no, or in this case, filtered back projection technique, to see the cross section. And that is how you use the tomographic reconstruction technique. And of course, you have to also remember the field of view and the resolution. No? Note that the nominal resolution of the reconstructed image can be described by the unit voxel size. So the spatial resolution is typically greater than the voxel size because it depends not only on the geometry but the other factors. In this case, a smaller field of view would give you a smaller voxel size or better nominal resolution given the fixed detector size. And later on, I'll show you some examples of this. And this is an example on how you communicate with the computer. When you look at this data, the image, of course, we can understand the subjective quality, what it looks like, because you have already a prior information. But when you communicate with the computer, we are looking at actually, it's an array of voxels containing some numbers. And these numbers, of course, we can plot this. We can measure the histogram. It's basically the grayscale value. This is the numbers associated with the voxel. Okay. And this is the frequency. And this histogram could give you somehow the different phases, major phases involved in the image. And this is an example of the histogram wherein we can separate the solid phase and the void space, which is actually have a GSV value of 0 and near 0. So this is how you interpret the histogram. And this is very useful because later on, we can use this to improve the image by linear normalization or by contrast enhancement. So this is basically adjusting so that we can maximize the information and subjectively have a better image. So this is one way. And of course, the most important analysis that we have to do is on image segmentation. So segmentation, the word itself, trying to segment. In this case, if we are trying to separate two phases, we are segmenting this into void space and solid phase. And one technique is thresholding. So there are many image analysis techniques, but just to give you some idea on how we can do this in image analysis. For example, let us consider it's a 10 by 10 matrix. This is an example of an image. And if you look at this image, in terms of numbers, the grayscale values, if we put a threshold value of 55, 55 and less will be, let's say, the void, then we will convert it into 0. The rest will be solid and image as white. So we can convert it to 255. So that is basically the idea of thresholding, using a threshold to separate the void from the solid. And additional analysis would be including a multiple cluster labeling algorithm, because sometimes we need to find out this as objects. These objects, for example, one cluster could be considered as voxels that are connected with each other. So in this case, using multiple cluster labeling technique, we can label this, into let's say default label 0 is a solid, then label 1, 2, 3, 4, 5 is the clusters, and they are connected, using, for example, a 6-point connectivity rule. In that case, the faces are connected, then they are considered as part of the one cluster. Okay, so this is how you can look at this multiple cluster labeling technique. And this is important because later on, when you try to measure some properties of the objects as a group, as a cluster, then it will come in handy. So this is the typical image data analysis workflow. Because of the, how I would say, during my time, when I did this, it's highly computationally intensive to process and analyze the 3D data. We have to use the volume of interest to reduce the size so that it will not be so computationally intensive. And this is just an example of the volume of interest, or your VOI, from this original city image. And this is the typical workflow. You try to segment it so that you can identify the void space, and then you do some labeling of the void space, And of course, you can also do some 3D volume rendering, wherein you can identify, for example, in my case, I'm interested with the largest percolating pore space. So this is how you typically analyze the data from X-ray CT. And of course, you can extend this by doing additional quantitative analysis. So let's have an example so that you can understand further on its potential application. So let's say I'll use microfocus X-ray CT, which actually will provide you a special resolution on the order of 10 micrometers. So your field of view is about 10 millimeter. No? So in this case, you'll have more or less a special resolution of 10 microns. No? And in this case, I'm trying to find out what could be the effect, how the environment such as the freezing thawing cycle could affect the microstructure, or what if we have a compresses induced damage the mortar, what will be the characteristics of the crack. So these are the things that you can do without having a physical cross section, but a virtual cross section, so that you can see the cross section of your concrete or your material of interest. In this case, I'm looking at the damaged mortar. So this is the information for the material of interest. I'll not discuss this in detail. You can check our papers on this one. But as I have mentioned, I'm interested to see the cross section of the fly ash mortar initially and after subjecting to freezing thawing tests. So here's an example again on how you acquire the image, the CT image, using microfocus X-ray CT. So this is your rotation stage. You place the specimen, let's say about 10 millimeter in diameter or 1 centimeter in diameter of this cylinder. And of course, you vary the specification so that you can come up with a better resolution. So in this case, I use, I think, a power setting of 130 kilovolts and 120 per microampere. And of course, through this scanning, the conical X-ray beam is emitted to the specimen, which rotates through 360 degrees. So, and it produced 1,500 projection images. I think it was recorded CCD camera with an array of 1024 by 1024 pixels. So that is how you produce this 3D image. And this is just an example of the slice. And of course, the quasi time resolved CT data at different freeze-thaw cycles. So you can see the formation of the cracks meandering around the aggregate cement interface. Of course, these cracks are imaged as black voxels, or very dark voxels in the CT image. And we can do some image analysis I have mentioned earlier so that we can extract the crack. And this is just an example. And of course, after extracting the void space, we can do some measurements. We can compute the void fraction, and we can compute as well the connectivity. As you can see here, the increased connectivity is due to the formation of the cracks, creating this additional void space in the damaged mortar. So we can compute that as well. And of course, we can do further study by looking at the volume interest that contains this crack network and applied additional sophisticated image analysis like the local thickness algorithm and the 3D visual axis transform or skeletonization. So with these algorithms, we can measure, for example, the crack width and come up with a crack width distribution out of this CT image. And of course, we can also try to measure the geometric tortuosity from the skeletonized void space. And this is just an example of this crack distribution in terms of tortuosity. And we can also extend this to quantifying the air voids. If we try to study the entrained air mortar, and in this case, this is just an example of some measurements that we can do for the air void size distribution. This is just an illustration on how we were able to generate the city images, and you can see some artifacts, an example of this, but you can still extract some data through some image processing analysis, no, at the vol of interest, and of course applied some additional image analysis techniques. This time we applied distance transform and watershed algorithm to segment and separate the air voids objects, no, as you can see here, no. We need to try to separate this so that we can have a better or accurate measurement of the air voids. Because of the limited time, I cannot discuss the details of the algorithm, but these are now pretty much standard in many image analysis software. So this is just an example of the air void distribution, and this is the another example for a compressed stress-induced downward mortar, where we tried to understand as well the crack geometry as shown in this slide. So this is the measurement that we have done for the cracks obtained from the compressive stress-induced damage mortar. So we can do this, of course, by properly extracting the cracks from the CT image. Another interesting CT image that I would like to share to you is the CT image of the pervious concrete, which I have shown earlier. And in this case, no, we can also try to visualize the connected void space in pervious concrete like this, and measure some parameters like the surface area, the specific surface, and even the characteristic size based on the local thickness algorithm. And finally, I would like to share to you the extension of my work on the quantification of tortuosity using synchronous microtomography. Because in this case, no, you were able to see, no, the pore space at the sub-micron levels resolution. And this is, I believe, important when trying to understand the transport properties of this cementitious matrix. And of course, no, we tried to subject to accelerated leaching test just to see, no, how the changes in the porosity, no, can be imaged, no, in the synchrotron microtomography setup. So again, the field of view is about a millimeter. So our sample here is very small, a shard of less than 1 millimeter, so that we can have a resolution of effectively about 0.5 micron, given the X-ray system we have. And this is the, the place where we have our synchrotron microtomography experiment. And of course, this is an example of the very small specimen that we have. I will not give you the detail of the setup, but as you can see, we use the parallel beam, no, from this setup. No? And in that case, we are able to find ways to image the cement paste at sub-micron resolution, like this one. This is through the cooperation with Obayashi Corporation, like Dr. Hitomi. And this for a 7-day cured cement paste, for the 28-day cured cement paste, for the deteriorated cement paste, and so on. So these are the things that we are doing. And of course, we extend this in quantification of the diffusion tortuosity. So tortuosity is, you could say that if a transport property is as simple as a straight line, when it's tortuous, it's not as simple as a straight line. And in this case, we try to quantify this, no, using this parameter known as diffusion tortuosity. So if you imagine the simulation of Brownian motion of a dust particle in 2D space for illustration, we can simulate this as well in a digitized pore space. And the restricted motion is due to the solid boundary. So this is just how we extract the data from the simulation, wherein we can measure the diffusion tortuosity. And we tested it first in something that we can track, no? Like a simple capillary model. Then, of course, we can do the simulation for a free space, 100% porosity. And of course, for some, we can also try this for an extreme situation where it's isolated, not connected. And you can see that we can estimate accurately this diffusion tortuosity using random walk simulation. So this is just an example of the random walk simulation. Some output from the random walk simulation, wherein it plot the mean square displacement against the lattice walk time. And we are trying to find out, of course, to compute the tortuosity is how dependent the mean square displacement to time. And from this, we can compute the tortuosity and try to correlate this with porosity if there is some trend or pattern. And this is just one example of this porosity tortuosity correlation. And of course, we extend this to measure other properties like permeability, wherein we have now the 3D image-based simulation. And you can check this paper if you would like to know more. And through these additional parameters, we try to propose a non-dimensional equation that relates this pore structure parameters and those transport parameters like permeability, tortuosity, with the characteristic size of the pore space, like a mean diameter of the pore. And we also tried, maybe Sugiyama Sensei will explain this to you more on how we can use contrast agent like cesium carbonate that could act as a tracer, where we could do some measurement to get some insights on the diffusion along the crack. So this is an example of this cesium carbonate being imaged, before and after it being immersed in this solution. And of course, there are many potential applications of X-ray CT as long as you have the imagination to find a problem for it. Prior to pandemic, I and my student trying to explore the self-healing capacity of geopolymer with microorganisms in it. And we tried to use X-ray CT, which we have now in a government institution. But unfortunately, because of the pandemic, this was suspended or delayed. So to end my talk, I think I would like to leave you some insights wherein if you look at the future, the possibility of trying to see such as the future that is unknown or hidden can ignite our imagination. And in this case, there is a story wherein the Hounsfield tried to find out whether it can detect hidden areas in the Egyptian pyramid by capturing the cosmic rays. How we can look inside the box without opening it. In fact, this is an interesting problem. And in our case, we tried to unbox by understanding the voids and cracks in cement-based material. If you have some useful idea about the future, don't worry if it appears to be ridiculous. In fact, there are many studies that you can see describing what the future could be in terms of the application of X-ray CT to concrete. Once again, thank you for your time. All of the data and concepts actually I presented and the references therein can be found in our most recent paper published in the Journal of Advanced Concrete Technology. I will be happy to get some of your feedbacks from and including questions, suggestions, and possible collaboration from you. Thank you for your time.
Okay, thank you very much for nice presentation, Professor Promentilla. So, sorry, time is coming. So I will move on to the presentation of Sugiyama Sensei. So after Sugiyama Sensei presentation, so panel discussion will start. So please wait a moment, Promentilla Sensei. Okay. So I will move on to the next presentation from Professor Sugiyama. So before that, I will introduce the brief introduction, brief biography of for him. So Professor Sugiyama is now a professor at Advanced Social System Group, Division of Civil Engineering, and Faculty of Engineering in Hokkaido University. So he obtained a PhD from the University of New Brunswick, Canada in 1994. His research interests are now in supplementary cementitious materials, durability of structural concrete, and quality assessment of cement-based materials. And especially He is focusing on development and application of high-quality X-ray techniques for cement science and concrete technology. So he is one of the pioneers for this topic. And he is currently director of Japan Concrete Institute and a past technical board chairman in the Asian Concrete Federation. And as for the research awards, he has been presented with many awards such as the Japan Concrete Institute Award, Best Paper Award in 2006 and 2014. Therefore, he has led the concrete materials engineering and expand the novel technique in this field to advance the knowledge of concrete engineering. So, Professor Sugiyama, if you are ready, please start your presentation, okay?
Okay, so can you hear me?
Okay, no problem.
And thank you for your introduction. Hello, everyone. I am Sugiyama. Today, I'm very pleased to be given this opportunity to talk about this topic. So, Promentilla has already explained the basis of the development of X-ray CT, including the history. So my talk today is rather focusing on the concrete experiment. So here is today's content. This topic selected for this talk are based on our recent and past experiment using X-ray CT. First of all, I'm going to explain and introduce the concrete steel bar interactions, which include the corrosion of steel bars. And also, I will talk about the cracks in concrete around steel bars under tension. Also, I'm going to talk about the pore structure. Here, specifically, the use of local thickness algorithm, which has been already introduced by the Michael in the previous presentation. I'm going to show you a little bit another aspect to quantify pore structure using local thickness algorithms. This can include crack space distribution, as well as visualization of ITZ, interfacial transition zone, between aggregate and bulk cement paste. Related to this pore structure, I will talk about the transport properties. Here, again, Michael in the previous presentation has already explained a little bit. I'm going to show you a little bit details about this topic. So cesium carbonate solution is used as a tracer so that the X-ray can trace this clearly, giving us the more contrast, differentiating from the cement-based materials. Finally, I will talk about the non-destructive integrated CT XRD method, which has been developed in 2013 using Spring8, Hyogo Prefecture, Japan. This is the first non-destructive method that can allow us to conduct CT measurement. At the same time, XRD can be conducted targeting to the interest regions. So, organizer of this JSCE webinar asked me, please explain why do you use X-ray CT? What is the advantage to use X-ray CT over conventional microstructure method? And here is, I think, the answer. The desire to see through what is invisible is a desire of many. In the last slide of my presentation today, I will also say this word because this is the our will to use X-ray CT for the research as well as industrial applications. So this slide was taken in, I think, the Frankfurt airport when I visited to Germany. So you can see the car automobile is cut in half so that you can see the main part of the automobiles, engines. But this is a destructive. Then desire to see through what is invisible is a desire of many. So here is X-ray CT scan result for the automobiles. And also this is the hidden inside of the room, but the X-ray can detect what is existing, what is present inside the room. So here is a utilization of the X-ray CT. So non-destructiveness is a utmost advantage by using X-ray CT. So category of X-ray tomography is explained in this slide. First of all, the medical CT. Almost all known, the medical CT is now very important apparatus to diagnose such as human body. Then the size of the medical CT is allowing for the human body size. In case of the X-ray energy is a 40 to 60 kilo electron volt, and the resolution is 0.1 to 1 millimeters. But of course, if you use for the human body, low exposure is required. Also, the high speed measurement and high definition are also required. On the other hand, for the industrial and research purpose, mostly the micro CT is very much advantageous. But you have to sacrifice the size of the materials. Then size can be small, like small parts, and microstructure studies, and at the same time, the finding a defect such as voids and cracks. So when you use micro CT, normally X-ray energy range from a few kilo electron volt to the 100 kilo electron volt. That allows us to see inside at the resolution of 0.1 to the 10 micrometers. And of course, for the micro CT, particularly to use for the research, high resolution, quantification, and element selection and so on are required. So here's some notes. What is a possible future use of this micro CT? Of course, exploration of the mechanism that can relate to the durability of the concrete. You like to know the mechanism, what is going on inside the cementitious material. By knowing the mechanism, you can improve the durability of cementitious material. So micro CT is in the past and in the future. The exploration of the mechanism is one of the biggest goal for use. This may include the finding of the defect, like again, the voids and the cracks. And also the 3D image-based simulation is nowadays developed in the other field so that simulation can be conducted based on the rather real material inside that can obtain from the X-ray CT measurement. And future utilization may be related to the 3D printing based 3D printing studies, because this information can be given by the digitized 3D data obtaining from the X-ray CT. Industrial and research purpose, others is also categorized here that can be used for the rather large products and parts. Because of the larger size, the X-ray energy increased, say, the 1 mega electron volt. But at the same time, you have to sacrifice the resolutions, 0.1 to the 1 millimeters. By using this X-ray tomography, you can find the defect detection, length, and waning measurement. So here can be used for the inline CT. This would be explained in this slide here. So inline CT is conducted for reject-free productions. Nowadays, a precast concrete or precast member is recommended to use in order to increase productivity for the construction site. Then for making precast concrete, 3D printing will be applied. But in the same factories, X-ray tomography is used in line, so that this precast product is going through the X-ray tomography, finding any like a defect. Then if you find a defect, you go back to the production site. So that is a feedback, and this may be possible for the use of the inline CTs. And as far as Japan is concerned, the high energy X-ray tomography is now used, that is up to 9 mega electron volt. Using this high energy X-ray tomography, you can measure for the size of the object larger than 300 millimeter, even for the steel materials. And the field view of diameter 600 to 800 millimeter and height 500 to the 1000 millimeters. And the weight is 100 kilograms. So this rather large object is possible by using a higher energy X-ray tomography. This is very good opportunity for concrete technologies. On the other hand, synchrotron X-ray micro CT, especially for the research purpose, in Japan, Spring 8, Aichi Synchrotron Radiation Center, satellite source are already in service. And another facilities will be planned in Tohoku. So having these facilities and operators, there is so many chance to use X-ray tomography for cement-based materials research and industrial applications. So let me talk about the recent development. Particularly the recent development is divided into the device development and software development. For the device development, so 4D CT, which is a dynamic imaging technique for CT along with time resolutions. And in-situ observation has been employed, such as deformation under external force followed by field destruction. So in addition to this, an environmental chamber with high lower temperature control sit on the CT stage has been also used for in-situ measurement. So these are now challenging for the use of the cement-based materials. But the software development is also necessary to use the most advantageous sophisticated materials coming from the device development, such as data acquisition systems, because the data volumes is increasing when the method and detectors become more sophisticated. Then more progress in labor saving and automations are now in progress, where the possible from data acquisition to the processing is expected. So regarding data processing, AI and deep learning method are being developed. So then in parallel with the device development as well as software development are necessary for advanced X-ray tomography method applied to the material research and industrial applications. So brief explanation of the application of the X-ray tomography for the corrosion propagation monitoring. So here is a specimen used for this study. So height is a 210 millimeter and width is 100 millimeter and length is 350 millimeter. So this element was simulated reinforced concrete slab so that you have a two-layer reinforcement, which is the size of the D19, and rather many reinforcement inside specimens. And the total weight is about 20 kilos. Using these specimens, the NaCl solution applied on the top. And here is a change in the half cell potential monitoring. Then after finding some drop of the half cell potential, we took these samples for the measurement of the X-ray CT. So here's a one shot. So you can see the inside concrete specimens of this rather bigger size of the specimens. And if you look at these specimens, you can see the some kind of the corrosion product around the reinforcement on the top of the reinforcement. But I think this is the kind of a limitation for finding corrosion materials by using X-ray tomographies. Here's another shot for the detection of the corrosion around the reinforcement. So here is a line profile CT values. If you define what is a corrosion product based on this line profiles, you may say the Y here is a CT gray value, which is equal to the CT values. So a little bit higher than base CT values, you may define here as a corrosion product. Then you can change the colors to show more clearly in color for separating corrosion and reinforcement. But what do you find? Seems to me even in this method, it may not be good enough to find the corrosions. But you can see clearly this is the binding wires. So binding wire shows some corrosions. And this is the upper reinforcement, and this is lower reinforcement. And here is rather dark things may relate to the corrosions. And the dark blue here, this is identified as a corrosion based on the line profiles here. But seems to me this may be the limitation at this point by using high energy X-ray tomography for the detection of the natural corrosion test in the concrete. And this corrosion study is also conducted for detecting the corrosion phenomena by X-ray tomography. So in this case, accelerated corrosion test is conducted. So here are the specimens, cylinder specimens, 200 millimeter height and 55 millimeter diameters. And rather upper areas, you have a reinforcement, which is a D10s. And the electrical acceleration test conducted under these conditions. And after this electrical applications, X-ray tomography was measured. So using these conditions for X-ray apparatus. So here's the results. Well, the CT image before and after corrosions. So here is the after corrosion test. This is a line profile starting from O here to the E. So you can clearly change in the line profile of the CT values. But of course, using this X-ray CT, you cannot avoid beam handling. You can clearly see some kind of the beam handling here. But even so, you can see the higher CT values like A here and E here. And this product might be related to the corrosions obtained from this accelerated measurement. Then you can separate and extract this corrosion product like this. Then you will find this kind of the contour pictures. Blue in bar, and the green here is a corrosion, and the gray here is cracks. Before testing the electrical acceleration test, specimen was cracked, creating fracture cracks in specimen, so that you can rather find the location of the corrosions. So you can see this is a before corrosion and after corrosion. This is the fracture cracks, and after corrosions, this is a fracture cracks again, and you can see some pitting the reinforcement here. And this is a closed CT image. So clearly you can see the reduction of the cross section of the levers like this. The upper figure here is actual specimens extracting after test. So compared to this real reinforcement, so a CT image gives us quite good results. Then we try some quantifications. So here is how much reduction occurred in cross sections. So in this case, about 15 square millimeter rubber was lost in cross sections. So this is quite interesting. And another finding by this test is that we repeat the test. I mean, I repeat the X-ray CT measurement after 2 cycles and after 5 cycles. So here's after 2 cycles. You can see some kind of a void here, but here is a starting point for the corrosions. And extracting the steels, by the way, you still have some kind of beam hardening. You will see the black dots inside the reinforcement. But at the same time, you can see here is a rather dark area, which probably the corrosions. And the difference image between two shows something like this. Then you can see more clearly on the corrosion product. So here's after 5 cycles, this corrosion developed more in reinforcement. So here is a difference image. The corrosion product was also found in another part of the reinforcement. Then reduction of the reinforcement cross-section was measured. So here's the location of the steels. So this is the increase in the cycle of the accelerated testing. You can see at the point of the crack, the reduction of the cross-section of the reinforcement is increased. So by using these methodologies, you can see the mechanism of the corrosion under accelerated testing. At the same time, you will have some kind of the quantification of the steel reinforcement cross-sectional reductions. So another topic is crack formation around deformed reinforcing burrs. There are many excellent research in the past. The cracks normally occurred near the reinforcement under tensions. So reinforcement bar under tensions showing some creating cracks because of ring tensions by knot creating a formation of crack. And this cracking provide easy access for transport through this crack. And finally, the bone splitting failure will occur. So this is very much important to know the formation and the development of the cracks around the reinforcing bar under tensions. So we developed some kind of unique sleeve bars that allows us to create the tension force around the concrete. Because of time, I'm not going to in detail, but this sleeve bar allows to induce the tension force around the concrete. So then at the several increase in the tension force, CT, X-ray tomography was measured at each step. And the focusing point of the X-ray tomography is here. So I can show you how the cracks around the reinforcement developed due to the tension in reinforcement. So clearly, the primary first crack occurred at the nodes of the reinforcement and increasing. And cracks occurred ITZ, the aggregate and cement paste. And the secondary crack is also occurring. So summarizing this research, here is a crack with 0.2 millimeter, the starting first visible crack here. And when the tension force increased, so crack width becomes 1.1 millimeter on the surface, secondary crack occurred. And crack width increased 2.1 millimeter on the surface. The separation of the concrete from the reinforcement surface occurred. So this kind of the phenomenon and observation are very much significant to know what is going on, the concrete surrounding the reinforcing under tensions. So pore size distribution and transport properties. Here's another topic, the local algorithms, local thickness algorithms applied that is used for quantify the pore size distribution, and also using by this algorithm, you can find the crack size distributions. Move on to the application of this algorithm to see the pore size distribution, particularly the ITZ. So first of all, here is a visualization of ITZ. So this is the bulk cement paste in the black, and this is the red here in the ITZ, and the green is in the aggregate. And this is the thickness algorithm. So you can see the quantified size of the pores in the ITZs. So having these data, you can conduct some kind of studies having the mean thickness of the pores in ITZ is 26 micrometers, and the sigma 10 micrometers, and max pore size in ITZ is 56 micrometers. So the use of the thickness algorithm provide us very much quantified analysis around the ITZ. So here is very good, very interesting research again on the ITZ. So this data was obtained from the synchrotron microtomographies. So having an onion layer algorithm that is developed, we found that the density in the ITZ and how the density is changing from the surface of the aggregate to the far from the aggregate. So here is the after the age of the specimen 1 month, you can see the near the aggregate surface, say the 10 micrometers. That is the minimum free densities, but 10% less than bulk cement paste. And density is increased with the age. And after 1 year, you can see improvement of a per size of the ITZs. I'm going to skip this one. And visualization of the transport phenomena in crack with a tracer using a cesium carbonate solution, which has been partially reported by the Michael Promentilla. So by having this kind of the mortar specimens, applying a bending moment that create the flexure crack like this, and the flexure cracks is also quantified by using local thickness algorithm and showing like this. And after having cracks, the cesium carbonate solution is attached on the bottom of the surface, and then this solution is going up. Then X-ray tomography was applied to detect the movement of this tracer element. Here is OPC concrete, and here is FA concrete. So you can see the rather sharp shape for the fly ash concrete. This means a diffusion coefficient, uncracked matrix is changing between OPC and FA as shown in this tables. So this methodology is also giving us some kind of a quantified assessment of the diffusion in cracks. So here is another applications. You can see the after crack occurred, you can see the cesium carbonate solution going inside the specimens, and the solution is accumulating on the bottom in the poor air bubbles here. So this kind of phenomenon can be detected by X-ray tomographies. So this is also another research on the transport phenomena in crack space, knowing crack geometries. So here is a different crack width on the surface. So time changing, showing how transport occurred into the crack space, the 1 hour, 3 hours, and 9 hours, 24 hours, depending on the crack width and the type of the specimens. This is also used for the quantification of the diffusion coefficient. So by using this kind of things, you can have the quantified diffusion or transport properties. So I think the time has already comes, but let me talk about these final topics, the non-destructive integrated CTXLRD measurement. So here is very much known, the cement hydrate classified by the linear attenuation coefficient. So having this cement hydrate type, theoretically you can calculate the black values in case of the 15 kiloelectron volts. So by knowing this, you may find what substance inside cement-based materials. So spot analysis can be possible by knowing rack values. But we found that this is not enough. Preciseness of the identification of the hydrate is not accurate enough. That is a big background of the development of this non-destructive integrated CT XRD measurement, which is developed in Spring 8 in Japan. So using white beam lined BL28B2. So here is the samples. So then the first is a CT measurement, and then this is a XRD detectors. I'm going to show you more details. The first of all, the CT, micro CT is measured using these systems. And based on this CT measurement, you can find the CT image. Then you can direct region of interest, which is appointed for the XRD like this. So by having this coordinate, you will conduct XRD like this. Then you will find what subject or what minerals inside the cement base at the particular position, which is a region of interest you selected based on the CT image. So here's a non-destructive integrated CT XRD method. So this method has a good advantage by having over the conventional XRD method. So normally XRD is the diffraction angles is changing for capturing the signals. This is a long measurement time is necessary. On the other hand, having this X-ray energy dispersive method, it's very quick. That is one point to be accelerate this testing method. Again, the both CT and XRDs. And having these methodologies, this method first applied to see the leaching phenomena through the cracks. So here is a CT image, and these dots are region of interest where you like to see by XRD. And then in total, 68 XRD measurement conducted in a relatively short period of times. And then by analyzing the XRD profiles, you will identify the location of the rich portlandite regions and rich calcite region like this. So then this methodologies gives us the microstructure changes, not only the geometrical point of view, but the mineral point of views. So this methodology is very much powerful for the research in the cement-based materials. So this, I think the time has been gone, but this is the final things. Again, why we are using XRCT for those cement-based materials, particularly the durability research. Again, the desire to see through what is invisible is a desire of many. So that is the answer for the use of this method. So summary of this method or the presentation today, you can find this paper, recent invited papers, that is also shown in Promentilla. So thank you very much, and sorry for longer times for my poor talking my presentation. Thank you.
Okay, thank you very much, Professor Sugiyama, for nice your presentation and showing us many research data. So all of these are fascinating and unique data for concrete engineering. So, but the future prospects should be discussed properly. So panel discussion will be open, inviting the Professor Asamoto as a moderator. So Professor Asamoto, can I pass this moment to you?
Okay, thank you for your introduction. I'm Asamoto from Saitama University. I'm also studying the material science of concrete, and then, but I'm not so much familiar with XCT, but I'm very impressed with both wonderful presentations. Thank you very much for your presentation. Actually, firstly from me, I very interested in the XCT, but I also understand some limitation, especially the resolution, 10 micrometer you mentioned, but many phenomena also related to the nanoscale, gel and so on. Of course, crack also important, but also when you measure some crack information, but on the other hand, also small power influence some durability. So how do you think this connectivity between the mesoscale pore to the nanoscale pore? Would you please give us the opinion from Professor Michael?
That's a very good question, Asamoto Sensei. In fact, this is one of the important topics in advancing X-ray CT systems, is to improve the spatial resolution. If you noticed when I presented the slide, nowadays they are now developing this nano CT, wherein you can see even at the sub-micron level to at least maybe at most 10 nanometers. No? So in this case, no, these are advancing, but again the limitation is the sample size. Of course, if you would like to have a very good spatial resolution, your sample size is very small as well, because that's the field of view limitation. And in this case, we have to ensure that the sample size will still be representative of the material of the test that you will be studying. So that's one of the considerations that we are looking at. The second one is the what you referred to as the image-based simulations. If we can develop like a multi-scale modeling in such a way we can capture the how you'd say the real structure at that level, and in more or less extrapolate at the lower level by considering some kind of physics like fractality of the structure and so on, maybe we can address this as well. But that I'm agree with you that these are the things that maybe future research should look at on the multi-scale process or multi-scale how would say geometry of the microstructure.
Yes, thank you very much. Sugiyama Sensei, could you give your opinion?
Yeah, some properties are related to the nano pores, and yes, once you may know what is going on in nano, you like to know what is going on into the sub-nano, something like that. So yes, but of course the X-ray tomography at this point, particularly for the cement-based materials and others, the limitations. Nano, or even in spring 8, the 100 nanos or submicrons are now available. So then if you like to see what is going on in the nano size, yes, we may need to wait until the development of the hardwares as well as softwares. Both are very much important for the development of the nano scale measurement. But yes, of course, there's a limitation at this point.
Okay, thank you very much. According to both your opinion, I also think even the micro scale we didn't know how clock distribute, how the microstructure change. Then nanoscale, even if we use SEM, it's impossible to understand connectivity and so on. Very local side, as Michael Sensei mentioned. Probably nanoscale, currently we can assume something, but you can also combine your measured, observed microscale. I think, as Michael Sensei pointed, and also Sugiyama Sensei said, even submicron is very difficult, but now currently you understand, according to your presentation, probably we can combine. Something can be assumed completely. Something can be realistic one. I think this kind of study also interesting. Thank you. And also, I'm very impressed with the Professor Michael's, your crack distribution and so on. But I also studying some pore structure. Difficulty is how we assume pore structure. This means cylinder or slit, or according to your image, it's a very complicated connectivity. So how you combine this information with diffusivity, this is the average material property. So this is, for me, it's a very challenging work. And then, of course, you propose some diffusivity equation and so on, but also slit pores or cylinder pores or, very complicated connectivity. It's how you think do such kind of, relation with material transfer information and your observed information.
Thank you, Asamoto, for your comments. Actually, no, even in chemical engineering, for example, because I am from that field, the concept of tortuosity is like a correction factor. It means you measure the macroscopic properties like permeability, because you cannot really see the actual pore structure where the fluid flows. So for you to fit the model that you measured, at the large scale, you use that as a correction factor. That's the past approach of measuring tortuosity. What we have now is we now have the capacity to look at the pore structure more or less, at that resolution, which we assume that at that scale, that micro scale, in fact, the controlling scale for the transport, probably, for example, for permeability and so on. So in that case, instead of having a tortuosity as a correction factor, you are now measuring it directly based on the real pore structure. And we propose diffusion tortuosity using a random walk simulation can capture that material properties. Right now, I think we were able to compare that with the other old technique of measuring transport properties like formation factor, which is actually applied in rocks. And it shows some correlation. And in this case, what actually we are looking at is how we can model, for example, the scaling up of these properties when you apply it, for example, in the beam. Because what we are modeling is in fact only on the how do you say, at the micron scale, but when you look at the beam, will it affect the properties when it comes to permeability and so on? So this is actually a research question that I have not looked at into in detail, but I agree with you that this is actually one maybe research question that should be looked at, and maybe the new generations of PhD students may consider this a very good research question as well.
Okay, thank you. Because my colleague also in the soil mechanics, they also studied tortuosity and so on using CT, but the scale size a little bit larger than concrete. But such kind of, porous media information, very, very interesting, both sides. But also in the case of soil, it's a particle, and then concrete is a solid material. So such is also more difficult in my feeling. Okay, thank you. And then, Sugiyama Sensei, I also very impressed your presentation of the 3D printing and also some defect learning. And then, when we have the defect, and then we can feedback to the 3D printing. Then I'm wondering, maybe you may explain, but what defect is it a defect due to shrinkage crack or construction error or 3D printing construction error? So your defect is what defect you mean? Could you explain again?
Yes, thank you very much. This inline CT is rather industrial applications. So in the manufacturing process, in case of the concrete, now the precast concrete is made in a closed factories, for example. Then in the precast, the lines, the large number of the members are produced time to time in lines, and then by having this kind of inline CT, you can find some kind of defect, the void or the cracks, but because of this early stage of the concrete mixing, for example, the space of each integrated layers, some kind of the errors are allowable or not allowable. So this must be specified. But by having inside structures without distracting, you can find good productions resulting in reject-free production. So this idea has been already applied to the other industries. So then if you apply this similar industrial application with X-ray tomography, one of the possibility is a precast concrete industry. And now precast concrete, for precast concrete, 3D printing is possible or promising methodologies for the productions. So then they combined these technologies. So those are the industrial applications.
I see. It's very interesting. So if you also utilize AI, artificial intelligence, you also may understand effect of mixed proportion and so on. Thank you very much. Then from audience, someone asks in situ, the site measurement using XRD. So I also interested in the possibility to apply the XCT to the real structure on site. So in the case of Sugiyama sensei shows very interesting corrosion detection. Then if we can also detect corrosion level on site, it's quite interesting. But is it difficult to use a portable CT machine, or I don't know?
Another possibility to use diagnosis inside in situ or the construction site or actual concrete structures. But one of the things is the higher energies. So then you have to look at the regulations in the public. So that is one things, because the target structure becomes large. This means that you need higher energies, and higher energies may not be always permitted in the public. And also the position of the detectors Most of the detectors is the catches the signals after X-ray coming through the specimens or the structures. Then the detector is the another side of the X-ray source. But some locations where the concrete structure is targeted, you may not have enough space to fit this both X-ray source and detectors. But nowadays, the movable X-ray systems within allowable X-ray energies has been developed in other institute. Then we will see the possibilities and also the resolutions. Even using higher energy X-ray tomography in our research for detecting the corrosions, seems to me detection of the corrosion on the surface of the reinforcement is not enough. I'm not satisfied with this. Then if you apply this into the real world, at this point, it may be difficult to detect the corrosions product developing inside reinforcement. Yes.
Thank you. Thank you very much. Sorry, I'm not so much familiar with this one, so, but I understand it's very difficult to apply currently, especially in large infrastructure. Michael says, do you have some opinion? So maybe in future, I'm not sure. So someone very interested in such non-destructive method, but maybe not, probably as Sugiyama sensei explained, it's still difficult, right?
Yes, I agree with Sugiyama sensei, because if you look at the basic components of an X-ray CC system, you need an X-ray source, of course, with enough energy to penetrate. Otherwise, you cannot detect the transmitted X-ray, which will be, of course, need to be detected by the detector. So you imagine you are placing this object. Of course, maybe in the future you can develop, let's say, a drone type like system wherein you emit this high-powered radiation. But of course, with respect to regulation, this is also another concern. In the same time, maybe with the detector in place, or maybe a different physics, we can explore that, but not exactly the same physics on what we are doing now at the XACC system. So I think maybe in the future, yeah, but not in the near future.
Okay.
I suppose, yeah.
Thank you. Some audience asked this point, so thank you very much for your answer. So some interesting ones. Sugiyama sensei shows some how materials penetrate into the concrete cracks through using the cesium carbonate. This kind of study very interesting, especially for example, water coming is very, very harmful for all concrete durability. So, and then according to Sugiyama sensei's study, so cesium can coming from the smaller pore or from larger pore. Probably general understanding from large pore is saturated, large crack saturated, then small crack moves. So otherwise it simultaneously penetrates into the side or not. So I'm wondering, so what kind of characteristic of liquid or solution penetration using your way?
Yeah, the cesium is the alkaline materials, alkali element. So its behavior is similar to the say the sodium. But if you use these solutions, this is a kind of the enhancing solutions, like the barium solutions for the röntgens for the body inspections. And the viscosity of these solutions a little bit higher as compared to the H2O. And actually, I am not investigate in details how much scale in pore size that the cesium can penetrate into, but having or by comparing OPC and fly ash mortars, which shows a different microstructures, and of course the fly ash mortar shows dense microstructures, and comparing the penetration depths in these two materials, definitely the OPC specimens allows more deeper penetration of this cesium carbonate solutions as compared to the fly ash mortars. Then for the practical point of view, these solutions is very much okay for detecting different transport phenomena depending on the microstructures under question. So of course the enhancing materials can be used with other types of the solutions, cesium chloride solutions or ionide, or the point here is detecting clearly, showing a good contrast, separating cement-based materials. So that is a cesium is one of the possibilities as a tracer element. So that's why I used.
Yeah, it is very interesting. So Professor Michael also you studies some random walk. This is some maybe simulation for the some water penetration or something. So I also interested in your simulation of some random walk and some diffusion. Or I'm not sure, but maybe also if you collaborate with Sugiyama Sensei again, it looks very interesting for me. How do you think this point?
Yes, yeah, that's a good suggestion, Asamoto Sensei, because if we can extract again this important pore space for the transport, and we can see, for example, how I would say disconnected pores and relate these properties, for example, the diffusion tortuosity, wherein we can do random walk simulation. Maybe we can check whether the diffusion coefficient that can be found in the material because of this tracer can be how to say verified, or more or less compared or correlated with this random walk simulation that will produce this diffusion tortuosity. Yeah, this is actually an interesting suggestion that we can look at.
Thank you very much. Yes, so almost time, so about 7 minutes. Takashi says that, can I continue the discussion or from JSC, will you say something? No?
There's no problem to
Okay.
continue there.
So, then, my question is almost, and also my interest is, as Sugiyama-san pointed out, corrosion product can be detected, and also can you also detect ASR gel by CT? ASR gel also very difficult to wear gel is lights, and then how it can create crack.
Yeah, of course, the ASR rims around the aggregate can be detected.
Okay.
having the ITZ study clearly showed the, of course, this is controlled by the resolutions.
Okay.
But the chemistry of the ASR gels can be good enough to separate the cement hydrate and ASR gels. But you may need some good eye to separate these. That's why we have developed the CTXRD method.
Okay.
For targeting region of interest. So in this case, the around the aggregate possible ASR generations, you can see some XRD signals, different thing from the cement-based cement hydrate. But these signals, I'm not sure this signal can be good enough for the ASR gel identifications. That is the question at this moment.
Okay, thank you. So almost time is over, but finally, I would like to ask both of you future of XCT research. I heard Professor Michael, you also study not only concrete as a material and so on. Now, currently in Europe, the wood is also one very popular material. I'm not sure wood also, I don't know, wood cell structure can be detected by XCT, but I would like to ask you, both of you, your opinion on future study of using the XCT. So first is Professor Michael, could you tell me your opinion?
Let me clarify your question.
My question is, what kind of is a future research utilizing the XCT, even the not only concrete, I mean even the other construction material?
Okay, so many potential applications of X-ray CT. For example, if you have another material of interest, in my case, I'm interested to find green cementitious materials like geopolymer. So geopolymer is actually doesn't use Portland cement, but use waste like coal fly ash and other aluminum silicate resources. So in this case, I'm interested to find out the microstructure of the geopolymer, whether it's similar to Portland cement-based material, or how we can elucidate the microstructure in terms of chemistry, in terms of pore structure, that can be important in the future, because we are looking at the sustainable concrete, wherein we can find some complementing substitute for Portland cement. So these are one thing. And you mentioned about wood. I think any material can be studied in X-ray, but we have just to adjust the specification. It could be soft or hard X-ray energy, because it will depend on how you would like to see the contrast between the different phases in the material. So in that case, for wood, maybe if you're interested with the, I don't know, for example, separating something in the wood, or knowing the composition of the wood, it's possible, I think, or even in new materials like composites that combine, let's say, wood, cellulosic fiber wood, and inorganic material like cement. So in that case, these are the interesting applications of X-ray microtomography.
Okay, thank you very much. Sugiyama sensei, you don't need to focus on the only wood, but you can also give us your interesting opinion.
Yeah, the X-ray tomography allows to study in a micrometer orders. So then we have to look at the increased productivity of the development of the new materials. At this moment, for developing new materials, you will make standard specimens and then put under the conventional test. So it will take months or years. But for studying with minute specimens, say the millimeter orders, X-ray tomography can be possibly find something answers for the development of the new materials. So as far as the research is concerned, yes, of course, the size of the specimen is one of the questions, but for developing a new materials, I think a minute samples in a millimeter order are good enough to use. In that case, the X-ray tomography is now used. And for the soft X-ray, yes, the spring 8 is a 8 giga electron volts, huge X-ray energies. But for the that is considered the hard X-rays. But for the soft X-rays, in the synchrotron facilities, you can use the Moores with this soft X-rays. In that case, the organic materials or more tissues is okay to use as a X-ray tomographies. So yes, the many possibilities are ahead of us.
Okay, thank you very much. I'm very impressed with both of your discussion and also presentation. Probably in civil engineering, we are not so much familiar with other state-of-the-art technology, such as XCT, and also, in my case, I also studied the SACS, X-ray scattering method, and such kind of combination of each information can clarify concrete complicated microstructure. And also, as you pointed out, probably we can also find new material, construction material, based on this kind of information. I'm very, very interested in your opinion and also presentation. Thank you very much. Now almost time. So Takai-sensei, shall we close and then as JC, could you close?
Okay, thank you very much, and thank you for this fruitful discussion of this topic, professors. So we can understand what is the right application, future prospects, and how to move toward deep knowledge for concrete engineering. So I hope it will be widespread for many researchers in near future. Okay, so I will be a little bit over, but I will close this webinar with informing about next webinar. So sorry, actually speaking, it was detail was not decided yet, but so it will be scheduled in the beginning of next year. Maybe we will have from January to March, but the topic will be on the structural side of concrete engineering. But the detail, if immediately after deciding the details, I will inform you later. So please look forward to it. And again, follow-up questionnaire for this webinar will be sent to those who have registered. So if you have time, please give us the feedback for this webinar. So again, thank you for all professors and all attendees for this seminar. And see you the next webinar. Thank you very much.
Thank you very much.
Thank you very much.
Thank you very much. Bye.
Bye.